Welcome to section 5.2 on double integrals over general regions. The goal of this section is to find the double integral of a function f of xy over non-rectangular regions. But before we can do that, we first need to look at how to classify regions in the plane. Subsection 5.2.1 Types of planar regions. Definition 5.2.1 A planar region D is called a type 1 region if their real numbers a and b and continuous functions g1 of x and g2 of x such that D is all of the points x, y in R2 such that a is less than or equal to x is less than or equal to b, and g1 of x is less than or equal to y is less than or equal to g2 of x. So what does that look like in the plane? Well, we have a boundary function above g2 of x, we have a boundary function below g1 of x, and we have x boundaries from a to b. So this type of region here that's bounded left-right by numbers a and b, and top-bottom by functions g1 and g2, that is a type 1 region D. Definition 5.2.2. A planar region D is called a type 2 region if there are real numbers c and d, and continuous functions h1 of y and h2 of y, such that D is the set of all points x, y in R2, such that h1 of y is less than or equal to x is less than or equal to h2 of y, and c is less than or equal to y is less than or equal to d. So what does that look like? Well, now the boundaries, the right-left boundaries are functions. h1 of y and h2 of y, they're functions of y. And the top and bottom boundaries are real numbers. C is the bottom and D is the top. So if a region in the plane can be described like this, with right-left boundaries as functions and bottom-top boundaries as numbers, then it is a type 2 region. So a remark, some regions are both type 1 and type 2 at the same time, while others are neither, but can be broken up into subregions that are type 1 or type 2, as we're going to see in the following examples. Example 5.2.1, we're asked to describe the region D between the parabolas here, first as a type 1 region, then as a type 2 region. So we're told that these are parabolas. That means that one of them is a x squared function, the other is a square root function, and if we take a look at the point where they are meeting, so that's the point 4, 2, then the top function here has the square root. The square root of 4 is 2, so this is y is the square roots of x. And the bottom function is some version of the parabola x squared, but if we square 4, we get 16, and so this must be 1/8 of 16 to give 2. So there's our two boundary curves written as functions of x. And so if we're writing this as a type 1 region, then we need our right-left boundaries to be numbers, and so they are going to be 0 and 4. So 0 is less than or equal to x is less than or equal to 4. And our bottom-top boundaries have to be functions. So 1/8 of x squared is less than or equal to y is less than or equal to the square root of x. So we can imagine going through the boundary from the region from the bottom boundary to the top boundary, going from 1/8 x squared up to root of x. So that's the region D as a type 1 region. Now as a type 2 region. A type 2 region, we need to have, type 2, we need to have boundaries on the y-axis that are numbers. So 0 is less than or equal to y is less than or equal to 2. And then the boundaries going left-right have to be rewritten in terms of functions of y. And so the x in the top, if I solve for x, I get x is equal to y squared. And on the bottom, I'm going to get x is equal to, well, it's actually the right if I'm considering this as type 2. X is equal to the square root of 8y. And so the leftmost boundary is y squared. That is less than or equal to any x value in between is less than or equal to the root of 8y. So that you can see, we can imagine x going from y squared to the root of 8y as we go through the region D from left to right. So there, D is both a type 1 and a type 2 region. Let's look at the next example, where our region will be neither type 1 nor type 2. So example 5.2.2, we're now asked to divide this region D into two type 1 subregions, D1 and D2, so that D is the union of both of them. So we're going to take our given region D and we're going to cut it right down the middle. And this might feel familiar to you from what you did in your integral calculus course. You're looking to match top and bottom boundaries if we're doing type 1. And so for this subregion here, which I'll call D1, the top boundary, which is the curve in red, and the bottom boundary in green stay the same. And then for the region over to the right-hand side, D2, the top boundary is the curve in blue and the bottom boundary is the curve in green. They stay the same. So D1, our region here goes from x is equal to 0 to x is equal to 1. I overwrote it there. So 0 is less than or equal to x is less than or equal to 1. And for any y value within that region, you can imagine y going up from the curve in green to the curve in red. And so the curve in green is the square root of 2 minus x squared is less than or equal to y is less than or equal to the curve in red, which is x. D2 is going to be the region right beside it there, and so that's from 1 is less than or equal to x is less than or equal to 2. And then the y values in that region will go from the green to the blue, and so from the square root of 2x minus x squared, which has to be less than or equal to any y value, which is less than or equal to the curve in blue, which is 2 minus x. And so there are our regions D1 and D2, and so D is the union of those two. Put those two together and you get the full region D. In the next video, we're going to see how we can use these types of regions to define, well, it's actually not a definition, but we'll see in just a moment, a double integral over these type 1 and type 2 regions. See you then.